So I had to change my talk a little bit since today's talk. How many of you have been to Dr. Zhang's talk this morning? Okay, so that's he presented a very comprehensive background into what personalized medicine and generally state-of-the-art techniques in therapies these days in the new century and where biomedical engineering is generally headed. Presented, so I will be, it really helps my presentation partially moving it forward. So keywords are really important, and this is a big title, so let's break it down into a few of the titles that we have as a plasmonic on-chip system, which is helped to characterize the perturbations in cardiomyocytes. So let's move ahead with these keywords. First of all, let's talk about a bigger perspective of personalized medicine. So if you look into personalized medicine, this keyword has been around for quite a while right now, so I'm expected that you guys are familiar with it. You probably have heard this saying that one size doesn't fit all. In these websites you go buy shopping. It's the same thing, but it's not the same thing with therapies for human beings. Every human being is unique, and right now we are understanding that better and better because of the technology advancements. And so it's really important that personalized medicine presents you with an option that you can tailor the treatments to patients based on their genes as well as non-genetic characteristic lifestyle backgrounds, like whether if not they do exercise, do they have a pet, do they smoke, drink. So ultimately, the word personalized medicine goes into the idea of cell and gene therapies these days. These cell and gene therapies are based on extracting the cells from the patient's own cells, which is blood cells or bone marrow cells, typically the renewable type of cells in the patient's body, which is least invasively extracted. They reprogram them genetically to a state of stem cells, embryonic stem cells, which then they can be chemically induced into a target type of cell, such as cardiomyocytes. So in terms of cardiovascular diseases, specifically cardiac arrhythmias, the new generation treatments is going into applying a cardiac patch on top of the patient's heart after a myocardial infarction or a heart attack generally, which is the hope for regenerating the patient's heart muscle with least chance of rejection, as well as an action towards preventive medicine for future occurring arrhythmias. So now, in terms of an in vivo application, before any sort of therapies that can be applied in vivo, you have to test them for biocompatibility as well as their toxicity before in vivo administration. So those kind of tests right now for cell and gene therapy goes into, and specifically for a cardiac patch, goes into a few ideas of contractility of the tissue, the conductivity of the tissue, rhythmicity of the tissue target, and its excitability. So monitoring all of these factors is where the idea of a heart on a chip, which was our second keyword, comes into play. So a heart on a chip device is actually a cell and tissue characterizing tool. A cell and tissue characterizing tool that is made out of a complex structure, 3D structure of co-culture of cardiomyocytes, contracting cardiomyocytes, fibroblasts, endothelial cells, which is all housed in complex, mechanically responsive and biocompatible scaffold made out of stromal cells, and is integrated with sensors to have readouts from it as well as stimulations. So a heart-on-a-chip device is, before we move on to the rest of the presentation, let me just talk about the scale, which is very important. We're going to be talking about cellular scale here. Scale really matters, so you have to adjust your perspective when using tissue versus a cell board, and those boards really matter. While your cardiac tissue might be in the range of a few centimeters, a cardiac cell is just a couple of microns to a couple of hundred of microns. And on the other hand, the ion channels, the voltage-gated ion channels, which are on the membrane of the cardiac cells, responsible for action potentials, are within a couple of tens of nanometers only. So we are going to be using plasmonics here, and plasmonics go within 200 nanometer sensitivity. Also, we'll discuss it a little bit later. So that falls into the range of cellular characterization and not that of a tissue. With that in mind, let's think about how a heart-on-the-chip device can actually measure the features of contractility, conductivity, excitability, and contractility, rheticity of the cardiac tissue, cardiac cells, cardiomyocytes. So microscopy is the lead, of course, bright field or fluorescent. However, the tagging of the cells takes a long time, but it is capable of extracting most of the parameters important for characterizing the cardiac tissue. And the other new generation technique is the microelectrode arrays, which have been around for probably 3 decades now, and in their advanced form. They are used as creative geometrical designs, which are used for monitoring the electrophysiological characteristics of a cardiac tissue, while the histological information is mostly provided with microscopy. Now, the type of the sensors that are embedded within these microelectrode arrays could be of a source of electrical, impedance-based, electrochemical-based, or plasmonics, which is our third scary keyword, which we're going to be discussing here. So plasmonic sensors have also been used in the case of monitoring cellular activity as well as electrical activity of live cells in people. What is surface plasmon resonance? So surface plasmon resonance is an optical technique which in terms of functionality is close to what a flow cytometry can provide you with, or ELISA in terms of molecular binding kinetics, but with a completely different optical background. A surface plasmon resonance device is made out of a gold sensor, which has a ligand bioconjugated on top of the sensor. Like this, please. On top of the sensor. And while an analyte is transferred using flow medium, and the kinetics of the interaction between an analyte and a ligand can be measured using surface plasmon resonance. Now, the technique fundamentally measures 3 concepts. One of them is molecular binding onto a metal surface. The other one is the refractive index changes near the metal surface. The metal surface is the gold sensor. And that near means 200 nanometers. Again, we have to ground ourselves every now and then. And the third thing is the dielectric property changes of the metal film surface. Now, based on the first 2 characteristics of the measures that the SPR device does, we hypothesized that maybe if we culture cardiomyocytes on a gold sensor and test it using surface plasmon resonance, we hopefully would be receiving a contractile signal, but we weren't unsure of where the source of the signal is. So we put cardiomyocytes on gold chips. We tested them using SPR device. Due to the ongoing ionic events during the contraction of a cardiomyocyte, which is opening and closing of consecutive voltage-gated channels, then there will be molecular binding, non-specific molecular binding on top of the metal surface, which is contributing to the first measure of the SPR. On the other hand, they do change because of the density changes due to the molecules coming in and out of the cells. There will be a localized refractive index change of the medium on top of the SPR sensor as well. Second measure of the SPR. And also, the flow medium is moved, the flow medium as a result of contraction of these cells, so they are electromechanically active. A contraction of these cells, the medium is also moved, and that movement puts another factor into changing the refractive index on top of the sensor, just like if you drop, rock in a pond. So you will see the change in light refraction. So we did see a contraction signal from the contracting cardiac cells using SPR. We called it the plasmonic eukaryotic signal. And eukaryote is a single cell, single cardiac cell. And because you're sort of getting an ECG from a single cell, we would call it the plasmonic eukaryotic, or the P-CeG signal for short. Now, to look more into the signal, we looked into breaking down the signal carefully, as Maria Carla presented, how decomposition is really important in terms of reconstructing the signal. We used wavelet transforms in decomposing our signal into its components, high-frequency components, and then reconstructed it based on the highest level of energy that our wavelet transforms had. The red one is showing a reconstructed signal on top of the previously original signal. It's really important to maintain as much as information as you can in biosignals because everything matters. Also, we did a short time Fourier transform, which is a depiction of how the frequency along time of the signal changes. This one on the left side, on the y-axis, you have a variation of the frequency in hertz. It is a 100-second interval time, and also it is the color-coded, the color shows the power and decibels of the frequency spectrum. So you can see that distinctly, you can see three colors across the line, like red, green, and a yellowish color above and below this one, which are the three main frequencies that we encountered in this event consecutively. And along 12 sample chips that we analyzed, here's the distribution that we saw, which they were insignificant. We couldn't find a significant difference because of a high variability that we had across different chips. However, we did see three frequencies across all samples. Now, to further understand what's going on with the signal and what's behind this rhythmic signal that we're receiving from SPR, we tried targeting the cell with specific drug treatments. First of all, we used verapamil, which is an antiarrhythmic drug, which blocks the calcium channels from having the calcium enter the cell. Calcium entering the cell, which will be responsible, calcium entering the cell will be responsible for cellular contraction ultimately. So by limiting the amount of calcium, you will be slowing down the event of contractions, ultimately stopping and halting the contractions if there's not enough calcium presented. The second drug was blevastatin, which is a statin. Technically, is used for myocardial. It's a myosin inhibitor that decreases the contraction of cardiac cells. When it's a myosin inhibitor, so what it does is it blocks the myosin head from connecting to actin and ultimately dragging on the cardiac tissue, which causes contractility. So decreasing the contraction effect of cardiac cells. And ultimately, we used caffeine, which interacts with an internal organ in the cell, organelle within the cell, which is the sarcoplasmic reticulum. It depletes the sarcoplasmic. The sarcoplasmic reticulum is a store of calcium. In case the cell doesn't have enough calcium, it releases it so that the cell can contract. When there's not enough calcium, when you induce caffeine, there will be a depletion of that calcium, so a stronger force of contraction is followed expectedly. So in all these three analyses, what we saw with the verapamil studies, which is to block the calcium from entering the cell through voltage-gated channels, we saw that there is the top one towards the left, the black, is the lowest concentration of verapamil, which is no verapamil. Then we have induced then we have induced 50 nanomolar, 100 nanomolar, and up to a 250 nanomolar verapamil, which you can see that there is an immediate decrease in the amplitude, which suggests that the contraction of the cells is affected because less calcium is available to the cells to contract. On the other hand, the blevastatin studies, which was supposed to stop the contraction signal of the cells, so again, while the cells are contracting, we have two events ongoing. One of them is the electricals and the mechanical phenomenon that is associated with the cell. So when you're when you're administering blevastatin, you're stopping the mechanical motion, but you are not halting any electrical ongoing events. So you still have an action potential going forward. You can see that this is an increase. This is an increase of the concentration of the blevastatin injections from 3 to 9 millimolars. And with increase of blevastatin concentration, you can see that we did see a significant decrease in the amplitude of the signal, which suggests that there is a portion of the signal is associated with contraction of the cell and can be subtracted from the signal possibly. And ultimately, we looked into the caffeine studies, which over time, by increasing the concentrations of caffeine from 2 millimolar all the way to 10 millimolar, there wasn't significant. There wasn't. I'm sorry. The amplitude of the signal was maintained. The shape of the signal was maintained, which is suggesting that the contractions were ongoing, and as you can see, that there's a drop in the full width half maximum, or the length of the signal. The time that the contraction occurs after administration of caffeine is because it depletes sarcoplasmic reticulum of calcium. It takes time for it to store calcium again and then release it. So we thought that by this we can conclude that the P-CeG signal is sensitive to real-time cardiomyocytes electromechanical functions. Detaching the cells, decomposing the signal is an essential component in understanding further how the signal operates. And why do we generally do all this is multiplexing right now, and we have to think about accessibility and affordability of these sort of state-of-the-art cares and therapies that we're talking about, gene therapies. So money is a big matter, and the Constitution for 2022, actually, the congressional budget for 2022 is asking to allocate $3.2 billion into personalized medicine because it is an expensive research. So it's really an important matter to decrease that cost so that we can propel the research much faster. A great thank you to NSF Summit and PANSUP, FIU, Graduate School, BME, all other as well departments, chemistry, materials engineering. My two amazing advisors, Dr. Antoine McGoron and Dr. Chin-Jong Lee, who is not here today. And also the great faculty of Biomedical Engineering Department, as well as my personal mentors. A lot of them are not here right now, but thank you.